Hello, welcome. This is question 2 for AQA'S A2 Physics. This is Unit 4, Section B, question 2. Okay, so the first part of the question asks us to state in words Coulomb's law. Now, I've put Coulomb's law in a box which says F equals K, Q1, Q2 over R squared. Now, this is exactly the same principle. Obviously, as I say, you substitute the mass for charge and the gravitational constant for the constant K, which obviously you know is 1 over 4 pi epsilon naught. Okay, so we explain it in the same kind of way. Okay, so the first thing you say is that the force is directly proportional to the sum of the charges. In other words, Q1 times Q2. All right. Your next point, you would say that the force is inversely proportional to the square of the separation. Okay. You would also say, that so you would say the constant of proportionality K is equal to 1 over 4 pi epsilon naught. Okay, unless you've already stated that in your answer. Okay, in terms of you already wrote it down in there. I would also state, now this is not necessarily asked in the question, it's only worth 2 marks, okay? So really I think all you need to explain are the first 2 points to get 2 marks, but I would state what the constant proportionality is, and if you get time at the end, it would always be nice just to add on to this part, okay? That's it can either be an attractive or a repulsive force depending on the charges, if one's positive, one's negative. Standard kind of stuff, okay? So, as I say, that's just kind of a recap on Coulomb's law, but really, all you need to do, really, I would say, is put them 2. If you're looking for the minimum you have to do, all you have to do is put them 2 points, I would say, okay? The last 2 I mentioned, stuff about being either repulsive or attractive, doesn't really matter, okay? And the fact that what the constant proportionality is, you don't need to mention that. What you do, I would, and I think I did, okay? But I think in the mark scheme, doesn't really mind. Okay, so that's 2A. 2B, we've got this diagram here, and what we've got is this distance 1 over r in meter per meter, and we've got volts on the vertical axis. Okay, and obviously 0, you've got 0, 0 there. Okay, and it's for a point charge Q. Okay, and r is the distance from the charge. Okay. State what can be deduced about the graph and how V depends on R, and explain why all values of V on the graph are negative. Okay, so this is quite a weird kind of question, but you have to kind of realise, well, what actually is this equation of the line? Okay, because it's a linear relationship, so we can kind of pick out some graph from this. Okay, so to do that, we have to realise, well, what actually is the relationship between these two? Well, quite clearly it's inversely proportional, because it's a constant gradient, okay, but this is 1 over r. If it was just r, okay, then it would be directly proportional, but it's inversely proportional, okay, so that's the first thing that you would state, okay, and obviously there's a negative relationship as well, okay, because obviously this has got a negative gradient. Okay, so you say V is inversely proportional to r. It's negative r, or something along those lines. Okay, and the reason, and then you need to explain why all values of V are negative. And generally, this will always be because there is an attractive force. Okay, there's 2 attractive forces, so this will obviously give a negative. Okay. Sorry, 1 second. Yeah. Okay, so there's only worth 2 marks. So your first mark is for stating about that the electric potential is inversely proportional to the separation. Okay, and why they are negative. And okay, you just say it's because they are both attractive or positive charges. Okay, both positive charges that are being considered, or something along those lines. Both positive charges. Okay, so that's your answer for 2B. Right, okay, so 2C part 1 says use a graph, data on the graph in figure 3 to show the magnitude of Q, okay, is about 30 nanocoulombs. Okay, now what you need to do is realise that the gradient of this, okay, is sorry, 1 second. I have to double check something. Okay, so sorry about that. Right, so this graph we've got here, obviously, I think I've been through this part of the question, so I do apologise. Okay, so the question says, state what can be deduced about the graph and how V depends on R, and explain why all the values of V on the graph are negative. So, in essence, what we've got to do is explain the relationship between V and R, okay, and why all the points on the graph are negative, okay? Let's start with that first one, why are they related? Well, I think I've already mentioned it here, said that the voltage is, potential difference is inversely proportional to the distance, okay? And you go, where does that come from? You might want to state it. It comes from the equation V equals KQ over R, okay? So that's where it comes from. Right, okay, so that's where it comes from. Now we can use this to answer later on questions, okay? But this little first bit, so as soon as you say that the voltage is inversely proportional to the separation, okay? The next point you're meant to state is the fact that they are both positive charges, which means they are repulsive, so this gives a negative potential difference, okay? Which is obviously represented on this negative graph that we see here. Okay, so they're the only 2 points you need to state for B, okay? 2C part 1 says, use data from the graph in figure 3, so that one, to show the magnitude of Q. Now the magnitude, which is Q, kind of important, is 30 nanocoulombs, and that's also important because it's nanocoulombs. Now it says about 30 nanocoulombs. That doesn't mean the answer we're going to get is likely to not be 30 nanocoulombs. It's likely to be near it, but it's not going to be 30 or 29.6 or something, okay? It's likely to be a little bit of a variation, okay? So don't be too put off if you do get a slight variation. Okay, so there's 2 ways you can answer this question, okay? Now, the first time I ended up recording this, I found out there's 2 ways halfway through my explanation when I was muddling the 2 ways together, okay? So, one sec. Because we want to work out Q here and relate this to the graph we've got on the to the graph of in figure 3. Okay, now I said that this is the same because it's a linear graph. Okay, we can use the equation y equals mx plus c, but as I say, because plus c is to do with where it intersects the y-axis, the origin, c is 0. Okay, so we could just say y equals mx. So because on the y-axis we've got v and on the x-axis we've got 1 over r, okay, this relates to the equation v equals kq over r, and obviously that's because of these 2 points here that we've mentioned. Okay, so as I said about the magnitude, we don't have to take into account that these are negative values. That makes sense because it's asking about the magnitude, okay? Right, because that's all the magnitude does, okay, it just turns it positive. Okay, so hopefully that's understandable. Right. So as I say, there's 2 ways. You can either work out, because I kind of showed it here, that on the y-axis we've got the potential difference, okay, which is this voltage here, kind of compared it there, and for the x-axis we've got 1 over r, which is, if you relate to this, okay, it's the bottom half of that, okay, so 1 over r is the x-axis, and we times that by m, so therefore quite clearly the gradient is k times q, in other words, k being that electrical constant we use, which is 1 over 4 pi epsilon naught, okay? Now as I say, you can either remember that, what that comes to, and I think it's something like 8.85 times 10 to the minus 12. Look at me. So yes, I'm just pathetic people who can't remember that. They're just so inadequate in this world. But yeah, I do agree they are, and that's me. I am one of those people. Because I probably just made that up. To be honest, in shorthand, I would just remember that because you give him what epsilon naught is, and you just worked out in the day. It's not going to take that much more time, and you're more likely to get it right. Well, I'm not, but you might be. Okay, so as I was saying, that's the gradient. Okay, so gradient is K times Q, so it's the charge times that. Okay, so two ways you can do this. Because the gradient is KQ, you can work out what the gradient is. Okay, obviously the change in potential difference and the change in the distance. Okay, or you can simply pick a point on this graph. Okay, so on the line, pick a point there. See what 1 over r is. Obviously, you need to do. You'll get a whatever that'll be. You need to do 1 over that to find out what r is. Okay, and you will work out the potential differences at that point. Okay. Now, at the point they used, okay, they said the potential difference was 2,000. Get that right. Oh, that was a good catch. Sorry. Come on, stupid thing. Yeah, okay. So they use 2,000 volts and the R is 0.125 meters. Okay, obviously they did 1 over that to get 0.125. Okay, obviously you just work out what that point is. Okay, so we know that is R and we know what V is. Okay, and as I say, K is this 1 over 4 pi epsilon naught, which you can simply just work out on the day of the exam. Now we've got the equation there, V equals KQ over R. So all it is subbing them into that equation now, okay? So V equals KQ over R, so as I say, we want Q, so you can either sub the numbers in and then rearrange, or just rearrange this equation. Okay, so it's probably easy to sub the numbers in, so we know the potential difference is 2,000 volts, okay, and obviously K is this constant, Q is something we want to know, and R is 0.125 meters, okay? So therefore, Q is equal to 2,000 times 0.125 times the times K, okay? Sorry, divide by K, which if you divide by K, yeah, all over K, okay? Because obviously we'll do rearrange, okay? So obviously this just comes to the fact that it's 2,000 times 0.125 times 4 pi epsilon naught, okay? Because obviously K is 1 over 4 pi epsilon naught, so 1 over that, okay, just gives the normal, okay? So again, just subbing them numbers in, and you'll get an answer of say you'll get an answer of 27.8 times 10 to the 9, okay? And obviously you just divide that by 10 to the 9 to get 27.8 nanocoulombs, okay? Which is what it's asked you. So you need to convert, when you get this answer, you will get the answer in coulombs, okay? You have to convert it therefore to nanocoulombs, and again, it's just times them by 10 to the 9 or divided by 10 to the minus 9. Okay, either way it's the same. Okay, so very easily just rearranging the equation with numbers. So nothing too difficult there. Okay, the next part of the question says 16 nanocoulomb charge is moved from a point where it is R is 0.2 meters to where R is now 0.5 meters. Okay, so there's a change of obviously there. 0.3 meters. Calculate the work done. Okay, so for this, just looking on the formula sheet for the equation. Okay, so the equation for work done, okay, is the change in work done, okay, is equal to the charge times the change in potential difference. Okay, right. So we want to know the work done. We need to work out the change in the potential difference. Okay, now. The change in obviously the charge stays the same, okay, that's a given, okay, but we want to know the change in potential difference. Now, as it's moved from a point where R is 0.2 to a point where R is 0.5, okay, we need to look what 0.2 was on here and look at the potential difference, okay, and then look at the potential difference where R was 0.5, okay, and obviously work out the change in that and then simply input it into that equation. So, just to let you know, the potential difference at 0.2 meters was minus 1,250, Okay, so the potential difference at 0.2 meters, as I say, was minus 1250. Okay, that was at 0.2. Potential difference at 0.5 meters was minus 500. Okay, now because obviously what we want to do is that's the potential difference before, that's potential difference after. Okay, so therefore it's quite clearly increased. Okay, by 750. Okay, so that's your change in potential difference. There's been an increase of 750 volts. Okay, so therefore the charge, well, because it wants it. Well, as I say, you could leave the 60 Coulomb charge and it's asking you to move in nanocoulombs. However, if you did that, then you'd have to change your units in the work done. So I think it's just easier just to change the charge, okay, into coulombs, okay. So the change in work done, okay, is equal to, well, you convert it from 60 nanocoulombs, 60 coulombs. It's 60 times 10 to the minus 9. Okay, and you times that by the change in potential difference. So, as I say, you're going from 1250 to 500, sorry, minus each one, okay, which obviously comes to 750 volts change. Okay, so therefore you just sub them numbers into your calculator and you get 4.5 times 10 to the minus 5 joules. Okay. Okay, so quite a simple calculation. Again, just using equations to giving it the formula sheet. So quite a nice question, nothing too challenging at all. Okay, so 2C part 3 says calculate the electric field strength at the point where R is equal to 40. Okay, I'll probably just have to rub this off, so I do apologise. Okay, so again, the first thing I would do is note down all the information you're given, and we can kind of see where we can go from that. Okay, so as I say, we're told we want to find the electric field strength where the point R is equal to 40. Okay, R is equal to 0.4. Okay, we also know the charge. However, the charge that you should use, okay, because I know this is why this question is a little bit confusing. I think it's actually given you. It's just asked you to work out the change, the work done for a 60 nanocoulomb charge. So you might think, oh well, I'll use a 60 nanocoulomb charge. Well, that was just kind of a different question, really. The main focus of this question, this graph, okay, is for a 27.8 or whatever we calculated in C part 1. Okay, whatever we calculated C part 1, that's the charge we're going to use here. Okay, so as I said, mine was about 27.8 nanocoulombs. Okay, and as I say, you want to keep that in charge, coulombs, which was 27.8 times 10 to the minus 9 coulombs. Okay, because we want SI units. Okay, so are you going to say anything else? No. Okay, so we have to work out the electric field strength from that. Okay, so again, it's just using equations from the formula sheet. Okay, so E is equal to KQ over R squared. That's the electric field strength. Okay. Okay, so obviously, as I say, K is this 1 over 4 pi epsilon naught, right? And Q, well, we've got the Q here, and we've got the distance R. Okay, so again, it's just inputting numbers into the formulas. So the electric field strength is equal to K. So I'll just write it separately: 1 over 4 pi epsilon naught times Q, which is, remember, keep it in SI units. So 7.8 times 10 to the minus 9 coulombs. Over R squared, I just put 0.4 brackets squared. Okay, so therefore, again, subbing numbers into your calculator. Okay, so you would get an answer for the electric field strength as 1560 volts per meter squared, or you would, if you rounded it up, you could get 1600 volts per meter squared. Okay, now obviously there's other ways of calculating it as well, that's just one of them, but I think that's quite a simple method. Okay, so again, just calculating field strength equations. Okay, now if you're not, if I made that up and I wasn't on the formula sheet, okay, because F equals QE, okay, and you want E, well, this is F and that's equal to QE, you want E to divide both sides by Q, so KQ over R squared is what we've got here, alright? That's how you get that equation if it's not on the formula sheet. But as I say, that's very standard kind of question, nothing too difficult. I would say the only thing that troubles you, you might have used the 60 nanocoulomb charge instead, okay, of that. Well, you'd only get penalised once, so you'd only lose 1 mark if you put the 60 coulomb charge. But again, if you put nanocoulombs, you put these units, then again you would lose a mark for your answer. Okay, so just be aware of that. Just a bit of accuracy, really. That was kind of one of the questions they did try and trick you up. Okay, so that's the yeah, you could have used a graph as well, but as I say, it's just something numbers, it's a lot easier. Okay, so thanks for watching. It's the end of question 2, and we'll see you in question 3. Thanks for watching.